Welcome back, method students. In today's videos, we're going to be having a look at sketching sine and cosine graphs again, but these graphs have got some translations in them. So either some vertical shifts where we have a plus k at the end of our rule, which if k is positive moves it up, if it's negative moves it down, and or a horizontal shift where we have an x minus h, x minus some number, or x plus some number in the bracket, where we know that if it's x minus, say 3, it's going to go 3 units to the right. If it's x plus 2, that's going to go 2 units to the left. Little note here, which will come in handy for some of the trickier examples. If the equation's got a coefficient in front of x that's not 1, right, so sine of bx minus c, always a good idea to take out that value as a factor so that x has a coefficient of positive 1, and that helps us pick out the horizontal translation. So that's just what that note is about. As I said, we'll come across that when we get to some of the harder examples. Okay. So we have already looked at how to sketch sine and cosine graphs just generally in terms of amplitude and period. We just haven't really introduced these horizontal translations so far. So in this question, we're told that we've actually got the graph of y equals sine x shown on this axis, just as a bit of a reference for us. And we're going to use it to help us sketch the function f of x equals sine of x plus pi on 4. So you can see that's exactly the same function, just that x plus pi on 4 is going to translate the graph pi on 4 units to the left. So we might even just make a little note of that, a mental note that it's going to go to the left by pi on 4. We know from our knowledge of amplitude and period that the amplitude is just 1. It's essentially a multiplier of 1 in front of sine. And the period of the graph is going to be 2 pi over n, and in this question n is 1. And so the period is just 2 pi. Okay, so let's have a look. All that's going to happen from our original graph of sine x is that all of these points everywhere along this dotted line are going to move pi on 4 units to the left. And that's kind of the method that we use to sketch this graph. So beginning from the origin, this point here is actually going to translate pi on 4 units to the left, and if we look carefully at our grid lines, each little grid line is pi on 4 units. So I want to mark my new points in red because that's what I'm going to draw the graph in. So this point here has just translated pi on 4 units to the left. We can take the first maximum here, and that just goes pi on 4 units to the left. This x-intercept at pi is going to move pi on 4 units to the left, and so on and so on. You can see how this works, right? So if we take each of our key points, and again, we're kind of using this idea of splitting the curve up into quarters. So in actual fact, I've probably got enough to just draw one cycle of this graph. Sorry, almost one cycle. This reference point here at x-intercept at 2 pi is going to come across here to this position. There's our first cycle, right? And you can see how we're just using that original curve to kind of build up a reference and then sketch in our translated curve. Now this question said to sketch the function from negative pi to 3 pi. So we've got to just take a few more reference points until we've filled in the graph all the way up to where we're supposed to sketch it. So this point at this x-intercept at 3 pi is going to shift over to here. Right, we can keep filling in our curve. Now, look, let's see. So this point here, when we translate it, this point doesn't look like it's going to be quite at the minimum. This will be our end point because that's the one that's going to map back to 3 pi. All right, and back at the other end, I've still got a little bit more to do. I can take this minimum here, translate that back by pi on 4. And again, if I'm looking for where my end point is, well, I can just take this point here, because I know that when that moves pi on 4 to the left, that's going to be sitting with an x value of negative pi, which is the other end point of my domain. All right, and so there's our kind of complete curve. The other thing, I mean, this is, I suppose that's probably enough to see what the method is about, but the other thing that we should be looking to do typically when we're sketching these graphs is to find some, label our x-intercepts and y-intercepts and also endpoints. So if we're going to do that, let's have a look at the x-intercepts first. The x-intercepts we can find by letting y equal 0 and solving. However, we can probably take a bit of a shortcut here. For example, we can see where the original x-intercepts were going to be, and all we have to really do is subtract pi on 4 from them. So for example, this point here, this first positive x-intercept, is just going to be pi, take away pi on 4. This point here will be x equals 3 pi on 4. And I haven't really had to solve an equation to work that out. So that's a bit of a time saver. This is going to get a little bit messy, but I'm just going to do some arrows here. So that point would be 3 pi on 4, 0. This point here is 2 pi, take away pi on 4. So that's going to be 7 pi on 4, 0. This point here is 3 pi, take away pi on 4. So really it's 12 pi on 4, take away pi on 4. It's 11 pi on 4. 0, and the first negative x-intercept, well, that just came from taking our point at the origin and moving that left by pi on 4, so this is going to be negative pi on 4, 0. All right, so that was a way we could find the x-intercepts. The y-intercept, well, even though this is a different type of equation to what we might have sketched previously, whenever you need to find a y-intercept, you let x equal 0 and solve for y. So if we do that with this equation, we've got y equals sine of 0 plus pi on 4. So y equals sine of pi on 4. Now we should know that one, but in case we don't, sketch a triangle. Remember that both of these angles are pi on 4, so it doesn't really matter which way we go. Sine's opposite over hypotenuse, so sine of pi on 4 is 1 on root 2, or root 2 on 2. All right, so our y-intercept, and this is getting a little bit messy, but I'll try to make it as clear as possible. Our y-intercept here is at 0, root 2 on 2. And the other points that we need to find, or that we often are asked to find and label on a graph, are the endpoints. Right, so we've got an endpoint at negative pi and at 3 pi. Now you'll notice that those 2 points are actually exactly 2 cycles apart. So both of those points should have the same y-coordinate, which means we only need to evaluate one of them. We don't have to find both of them separately. So for the end point, let's just use the positive one, maybe slightly easier. We're going to let x equal 3 pi, and therefore y will equal sine of 3 pi plus pi on 4, because we're just substituting 3 pi in place of x. And so, well, actually I'm not going to simplify that, because if I'm thinking about my unit circle and I've got 3 pi plus pi on 4, well, starting from an angle of 0, 2 pi is a full lap, 3 pi takes me over here, and then plus pi on 4 takes me down to there. So using a little bit of symmetry, I know that really what I'm working out is sine of pi plus pi on 4 down in the third quadrant. And so that's just going to be worked out by calculating sine of pi on 4, but because I know in the third quadrant sine is negative, I'm going to plonk a negative in front of it. And actually that makes sense, because from the endpoints we have, we know that the y-coordinate had to be negative. So that's just negative root 2 on 2. So the endpoint coordinate is 3 pi negative root 2 on 2. And over here, the first negative one, x coordinate's negative pi, y coordinate is negative root 2 on 2. Whew. And it looks like we've made a right mess of that graph, but I guess a lot to digest there. And hopefully, you know, you've got maybe a bigger graph to sketch on, or perhaps not so many key points to label, but I hope that gives you an idea of how we can use our knowledge of a more basic graph to apply a translation and sketch a new graph.